can see the slide. Okay, so today is about chapter 2. So chapter 2 is about the solving linear system. Okay, so here are the subtopics. So first is about the excellent form of a matrix, and then after that solving linear system, and the last one is finding inverse of a matrix. So I think most of it you learn already actually in STPM or matriculation lah. But we just go through, okay, in case you have forgotten about it already. Okay, so the first one is sorry, I forgot to record again. Let me do the recording first. Okay. Okay, the first one is on the excellent form of a matrix. Okay, so this is the definition of a reduced row excellent form. Okay, or simply we just say this is RREF. Okay, in short form. So an M by N matrix is said to be in RREF if it satisfies all the four criteria here. Okay, so the first one is all zero rows, if there are any, appear at the bottom of the matrix. The second one is the first non-zero entry from the left of a non-zero row is a 1. Okay, and this is called the leading one, okay, of each row. Okay, and the third one, for each non-zero row, the leading one appears to the right and below any leading ones in the preceding rows. Okay. Number 4, if a column contains a leading one, all other entries in that column are 0. Okay. So if a matrix satisfies all the four criteria, that matrix is said to be in RREF. Okay, and the remark here are any M by N matrix satisfying properties 1, 2, 3 is said to be in row excellent form. So, or simply we say REF. Okay, so the difference between REF and RREF is the number 4. Okay, the rest, number 1, number 2, number 3 is the same. It's just number 4. If it has number 4, then it is RREF, otherwise it is REF. Okay, a similar definition can be formulated in the obvious manner for the reduced column echelon form and column echelon form. So this is CEF and this is CEF. Anyway, normally in our course we focus on row echelon form. Okay, so column echelon form is very confusing for many of us, so we just deal with REF. It's easier, and to some of you it's already considered quite difficult. Okay, so next a few examples here. So determine whether the following matrices are in RREF. Okay, so number 1, A, matrix A. So we focus again on all the four criteria. So all zero row, if there are any, appears at the bottom. Okay, if you look at matrix A, there are no zero rows. So no need to consider requirement 1. The second requirement, the first non-zero entry from the left of a non-zero row is a 1. Okay. Okay, so if you look at each row here, the first non-zero entry is 1, 1, 1, 1. Okay, so requirement number 2 satisfied. Number 3, for each non-zero rows, the leading one appears to the right and below any leading ones in the preceding rows. Okay, So if you look at the first row, this is the leading one, okay, so there's no need to consider about it. Okay, next is the second row. So this is the leading one, so it appears to the right and below any below row 1, it appears to the right. Okay, same thing for row 3, it appears to the right of the second row, and then the fourth row is also appears to the right, and below the third row. So then requirement 3 is also satisfied. And then number 4, if a column contains a leading one, the all other entries in that column are 0. Okay, so if now we go column by column. Okay, so column 1, this is leading one, and then the rest all 0. Okay. Then column 2 is the same, leading one, the rest 0. Third column, this is leading one, and the rest 0. The fourth column, this is leading one, the rest 0. So A is RREF. Okay. So matrix B, so all 0 rows appears at the bottom. Okay, and then the first non-zero entry for non-zero row is 1, 1, 1. So it's okay. And then the second row, the leading one appears to the right and below the first row. For third row, this one appears to the right and below the second row. And then the rest 0, 0, 0, 0, 0. Then this is also RREF. Now this doesn't matter because there's no leading one in this column, in these two columns. And then the last one is matrix C. Again, all 0 rows at the bottom, and then the first non-zero entries is 1, 1, and then the second row it appears to the right and below the first row, and then this is 0, this is 0, this is 0, so this is also RREF. Okay. Now, next, determine whether the following matrices are in RREF. Okay, it's the same thing. Now, D, matrix D, this is not RREF because the 0 rows is at the second row. Okay. And then E is also not RREF because this is not 1. Okay. F, okay, so the 0 rows at the bottom is okay, and then this is 1, and then this is 1, but then this is not 0. Okay, so then this is not an REF. Matrix G, 0 rows at the bottom is correct, and then this is 1, 1, 1, appears to the right and below the previous rows, but this is not 0, this is not 0, so then this is not an REF. Okay. Any question? Leah?
No, sir.
No one? Okay, so this is the explanation just now. Okay. So we continue. Okay, determine whether the following matrices are in REF. REF is the first 3 requirements. Okay. So 0 rows at the bottom, and then this is 1, 1, 1, and appears to the right and below the previous row. So this is REF. And then this is no 0 rows. So, but this is 1, 1, 1, 1, appears to the right. Okay, so this is also REF. And J, 0 rows at the bottom. And then this is leading one, leading one, leading one, leading one, appears to divide and below the previous row. So this is also RDF. Okay. So next is the elementary row operation. Also, there's a different type known as elementary column operation. Again, normally we just concentrate on elementary row operation, ERO. Okay. Column again is quite confusing, but you can choose to use if you like to. Okay. Now, there are three types of row operation here. So the first one is interchange any two rows or any columns, and then multiply a row or column by a non-zero number. This is second type. And the third type is add a multiple of one row to another. Okay, in the form of notation. So this is how we write. So when you interchange rows or column, so this is the symbol. So it's a two-headed arrow. So here it means you interchange row I with row J, or you interchange column I with column J. Okay. And then if you want to replace row I by K times row I, so this is how you write. So you replace row I by K times row I. Okay, so meaning this is the old row I, and then this is what you want to replace to the new row I. Okay, so the third one is you replace row J by K times row I plus row J. So you replace row J by K times row I plus row J, meaning you multiply K to other row and then you do addition to the row that you want to replace. Okay, same thing for column, it's the same. So we go look at the example here. So this is a given matrix. Okay, so this is row 1, this is row 2, this is row 3. So if you want to swap row 1 with row 3, so you swap row 1 with row 3. So this is how you write it. So row 1 interchange with row 3. So you just swap the rows here, okay? You interchange two rows. And the second type is you want to replace row 3. This is row 3. You want to replace row 3 by 1/3 of row 3, meaning you want to multiply 1/3 to the row 3 and then you have a new row 3. So 3 divided by 3 you get 1. This is 1. And then 6 divided by 3 you get 2. And then -9 divided by 3 you get -3. Okay, so this is the second type. Now the third type is you want to replace row 3. Okay, you replace row 3 by -2 row 2 plus row 3. So basically is you multiply -2 to row 2 and then you plus this row. Okay, so -2 times 2 is -4, -4 plus 3, -1. So you have -1 for your new row 3. Same thing for the second column. So -2 times 3, -6 plus 3, -3. So you have -3 here. And then if you continue, -2 times 0, you get 0. 0 plus 6, you get 6. And then -2 times -2, you get 4. 4 plus -9, you get -5. So row 1, row 2, no changes. So you keep it as previously shown here. Any question for the row operation? I hope you understand.
So far, no questions, sir.
Okay. Okay, next is the row equivalent. Matrix B is said to be row equivalent or column equivalent to matrix A if B can be produced by applying finite sequence of ERO to A. So meaning if you apply row operation to any matrix, then the two matrices is considered as row equivalent. So for example here, so this is our first matrix A. You apply this row operation, you get a new matrix B. And then you apply again row operation, you get matrix C. And finally, you apply another row operation, you get a matrix D. So here we can say C and D are row equivalent. And then C and B is also row equivalent. And B and A is also row equivalent. And definitely D and A is also a row equivalent because you get D when you do a ERO from A. Okay, so that's the meaning for row equivalent. Now next is if you reduce a matrix into a row echelon form, okay, so every non-zero matrix A is row equivalent to a matrix in REF. Okay, so it's the same meaning as the previous definition, but just that when you do this, this is not necessarily in REF. But if you reduce a matrix into REF, that matrix is definitely considered as row equivalent to the original matrix. Okay. And then one thing you need to note here is that for any matrix, the REF is not unique. Okay. REF is not unique, meaning for any matrix A, there could be many types of REF depending on how you perform the row operation. But for RREF, for any matrix, RREF is unique. So meaning that for any matrix A, there can only be one RREF, no matter how you do your row operation. Okay. And next is the terminologies. So the first column with a non-zero entries is called a pivot column, and the first non-zero entry in the pivot column is called a pivot. Okay, so this is just the terminology. So for example here, we are given a matrix A. So the pivot column here is if you count from left to right, the first non-zero column is column 1. So then column 1 is called the pivot column, and then the pivot is this entry, okay, A31, because the first non-zero entry in the pivot column is A31. So A31 is the pivot. So that's the terminology. Okay. So next is more on the row operation. So how we reduce a matrix into REF. So for example here, we are given a matrix A. We want to reduce it into REF. And again, the answer for REF can be different. It depends on how you do your row operation. So one possible solution is this. Okay. So we are given a matrix A. So this is the original matrix A. Okay. And then we know that for the definition of the REF, the 0 must be at the bottom. So if you look at the column here, so we have 0, 0, we have 0, 0, 2, 2. So we need to make the first entry in the first row for the first column to be non-zero because we want the 0 at the bottom. Okay. So one way for us to do that is you swap the rows. Okay. So here I swap row 1 with row 3. So meaning you swap these two rows. Okay. Oh, okay, sorry. So you swap these two rows. Okay, then you have the new row 1, new row 3. The row 2 and row 4 no changes, so you just copy down row 2 and row 4. Now after that, remember the first non-zero entry here must be leading 1. It must be 1. So the only way is you replace the entire row 1 with half row 2. Or in other words, you just say, I want to divide the entire row 1 by 2. So you divide row 1 by 2. So you have 1, 1, -5 or 2, 1 and 2 here. Okay. And then row 2, row 3, row 4, no changes. So we just copy down. Okay. Copy down row 2, row 3, row 4. Now after that, I want to make this 0 because remember for the REF, everything here down here must be 0. So then the only way for me to do that is you replace row 4 by -2 R1 plus R4. So meaning you need to multiply -2 to this row and then you plus with the row 4 to get the new one. Okay, so -2 times 1, you get -2 plus 2, you get 0. So this is 0. Then -2 times 1 is -2 plus 0, you get -2. And then -2 times -5 over 2, so this is 5. 5 plus -6, you get -1. Okay. And then -2 times 1, you get -2. -2 plus 9, you get 7. 7. And then -2 times 2, you get -4. -4 plus 7, you get 3. Okay. So row 1, row 2, row 3 no changes. You just copy down. Then after that, we settle with column 1. Column 1 settle already. And then next is the column 2. We move on to column 2. So column 2, we start from all these 3 rows. Okay. Again, here you have 0 to -2. So I want to keep 0 at the bottom. So one way to do that is I swap row 2 with row 3. Okay. So you swap row 2 with row 3. So basically just interchange. So row 1, row 4, no changes. You just copy down. Now after that, I want to make this to become 1. So what you do is you divide row 2 by 2. So then you have 1. And then 3 divided by 2, you get 3 over 2. -4 divided by 2, you obtain -2. And then 1 divided by 2, you get half. So row 1, row 3, row 4, no changes. Then you copy down. So after that, I want to make this 0. So you do this operation. So you replace row 4 by -2 row 2 plus row 4. Okay. So then you will have have this lah. Okay, so we continue from here. Okay, so this is what we obtain. So after that, again, you need to make this to become 1. So how to do that is you divide row 3 by 2. Then you get 1, 3 over 2, and 2. Then after that, I want to make this 0. Then you apply this. So 2 row 3 minus row 4. To the new row 4. So then you get everything 0 here. Okay. So the matrix in REF is given by this. Okay. Again, if you go back and you try with your own row operation, you might get a different answer. So this is not unique. This is just one example only. Okay. Any question?
Okay, sir.
Okay.
No.
So next is the another example. Okay. So we go straight to the solution. Now, just now, this one is I do row by row, so you can see many matrices. So it's a longer work. Another way for you to write is you can combine many row operation together so that your work is simplified. You don't need so much space to write down your solution. So one example is you do like this. So you are given this matrix. So the first non-zero is already 1. Okay. So we don't do anything to row 1. So that's it, settle with row 1. So what we are going to do next is we need to make all the entries here below 1 or below row 1 to become 0. So everything must become 0, 0 here. So what to do is, so this is the row operation for row 2. This is row operation for row 3. This is row operation for row 4. This is row operation for row 5. So we combine them together and then we do one by one and it saves space. Okay. So for row 2 is you multiply -2 to row 1 and then plus row 2. So multiply -2 to row 1. So -2 times 1 plus 2, you get 0. Okay, and then -2 times 1 plus 3, you get 1. -2 times -1 is 2. 2 minus 5, -3. And -2 times -3 is 6. 6 minus 4, you get 2. Okay. And then -2 times -1, you get 2. 2 plus 1 is 3. Now the same thing for row 3, row 4, row 5. So you go back, you can try yourself. Then after that, we settle with column 1. So we move on to column 2. Now for column 2, this is already 1. So we don't do anything to row 2. So what we need to do next is to make this 0, 0, 0. So we need 3 row operation. So this is row operation for row 3. This is row operation for row 4. This is row operation for row 5. And then after that, we get everything 0. And by chance, we also obtain everything 0 here. And then we move on to column 4. Okay. Column 4, this is already in 1. So we don't do anything. So next is we want to make this become 0 and 0. So we need another 2 row operation. So this is for row 4. This is row operation for row 5. And finally, we get 2 0 rows at the bottom of the matrix. So this is the REF. Okay. So this is the solution for the example. So I don't explain step by step. Later on, you go back, you watch the recording, and you try to get it by yourself. So if you have problem, then maybe you can discuss it in your tutorial with your own group lecturer. Because it's quite difficult to explain this step by step online. Actually, it will be better if we do it during physical class. Okay. Let me see, there are some comments here. Okay, but seems uni punya more complex. Yes, yeah. Uni punya the matrix size is bigger lah. Okay. And more room for careless mistake. Correct, that is correct, more room. And the most challenging part for the raw operation is not the raw operation itself, is when you deal with, I think is when you deal with something like this. When you have a fraction, okay, when you have a fraction, you are more prone to do careless mistake, especially if you cannot compute the fraction arithmetic in your head. You have to do calculator, then it will take time lah, and sometimes you may key in the number wrongly. Okay. Okay, let me see. So we continue. We already. Okay, we stop here just now. Okay, next is the reducing a matrix into RREF. So far, we only reduce it into REF. So next is we want to reduce it into RREF. So as I say, RREF is unique. Okay, so you can only get one RREF for any matrix. So for example here, so find a matrix in the raw reduced raw echelon form. Okay, that is raw equivalent to matrix A. Now this is the same matrix as before, as the previous example, where we already obtained the REF. So this is the REF, okay, where we stopped just now. So to get REF, we just continue from here. So what you need to do now is basically you already obtained leading one. The next step is I want to make this 0 and this 0. Okay. So to make this 0, okay, so normally we do from right to left. We don't do from left to right, meaning we start with column 3 first. And then after that, we finish with column 4. Okay. So that's why for column 3, I want to make this 0. So then you need these two raw operation. Okay. Then you have 0 here. Again, as I said, the most challenging is when you have a fraction. So you need to be careful when you design the raw operation here. Okay. So once you obtain this, the last step is I need to make this 0. Okay. So how we do it? We have this raw operation. So finally, you have leading one, and then the rest 0. This is 0. This is 0, and then this doesn't matter. Okay. So then we have a RREF. So this is the RREF for the matrix A. Okay. Now, the second example is also we already did halfway, where we have reduced it into REF. Okay, so the next step is we need to make this 0 and this 0, because this is the leading one, this is the leading one, this is the leading one. Okay, so same thing here. So the first step, we start from right to left. So we want to make this 0. So using these two raw operation. Then after that, finally is this 0. And then with one raw operation. And this is the RREF lah. Okay. Now, if you look at this example, basically is we start from REF and then we go to RREF. But in exam or in assignment later on, if a question asks you to get a RREF for a matrix A, you not necessarily must have REF. Okay, you can do your row operation to obtain the REF directly. So meaning you no need to find REF, you can straightforward find REF. Because if you want to find REF, your work is longer. Okay, but if you want to be safer, then you have to do REF first. Do it slowly. For the raw operation, better to do it slowly than do it quickly, but with many careless mistakes. Okay. So that's the raw operation with RDF and RDF. In for the RDF, if you want to obtain it directly without getting through RDF, maybe later in your tutorial you can ask your group lecturer. I don't want to show it here. I'm not sure we got time or not. So it's quite difficult. I have no space to write here. So if physical, it will be easier. Okay, so next is the solving linear system. Okay, linear system. So there are two methods here to solve the linear system. One is called the Gaussian elimination. The second one is Gauss-Jordan reduction. Okay, or just simply Gauss-Jordan method. Now, these two methods basically very similar. The only difference thing here is the first step. So for the Gaussian elimination, in the first step, you transform the augmented matrix to a matrix CD in raw echelon form. And then you solve the matrix CD using back substitution. For the Gauss-Jordan, you reduce it into RREF, and then you get the solution with final step, which is the back substitution. Okay. So before that, we need to discuss more on the type of the linear system, three types of solution of the linear system. As I mentioned last week, for any linear system, so we have three types of solution. One is unique, the other one is many solution, the third one is no solution. So how does it look like with a unique, many solution and no solution? So we look at it one by one. So the first case is unique solution. So let's say we have a following linear system. Okay. So the augmented matrix is given by this. So as I said, this is a coefficient matrix. This is matrix B. Matrix B is the right hand side, and then this is the coefficient matrix. You take the coefficient and you form the matrix A. So if you transform it into RDF, okay, so again, this is for your exercise. So the RDF form is this, okay. So using back substitution means we start with bottom row first and go upwards. So if you look at the unknowns, we use X, Y, Z. Here it means this column is for X, this is for Y, this is for Z. So back substitution means we start with third row first. Okay, from the third row we have Z equals to 3. Okay, so then we have Z equals to 3. And then after that we go to second row. So from the second row, here we have Y plus Z equals to 2. Okay, and if you rewrite, you get this. Y equals to 2 minus Z, and then Z equals to 3. So 2 minus 3, you get -1. And then after that, finally, you do with row 1. So for row 1, basically, you get X plus 2Y plus 3Z equals to 9. So if you rewrite, you get this. X equals to 9 minus 2Y minus 3Z. So substituting Y, substituting Z, and then you simplify, you get X equals to 2. So the solution is x equals to 2, y equals to -1, z equals to 3. So this is the unique solution because you only have one set of solution. One value for x, one value for y, one value for z. So this is unique. Now, normally for any system, if you look at this matrix, if you look at this matrix, for unique solution, number of variables is always equals to number of non-zero rows. Okay, number of variable means number of non-zero columns. So if you look at the matrix here, number of variables, so we have x, y, z. So this is 3. So this is equals to number of non-zero rows. So if you look at the rows, these are all non-zeros. So you have 3 rows. So 3 equals to 3. So we have a unique solution. That's the characteristic of a unique solution. Next is the many solution. Okay, many solution. What it means by many solution is in REF you have something like this. Okay, so basically you have 4 columns and then you have 3 rows. 4 columns, remember the columns refers to number of variables. So let's say this is x1, x2, x3, x4. Okay. We do back substitution means we go upwards. We start with row 3 first. So from row 3, I have x3 plus x4 equals to 3. Okay. So if you rewrite, you get this. x3 equals to 3x minus x4. Okay. And then, but I don't know what is x4. You don't know then, because we do not know from the system here. So what we can do is we assume. So we assume x4 equals to r. R is any real number. We don't know what r is, but we just assume that x4 equals to r, and then r can be any real number. So the solution for x3 becomes 3 minus r, where x4 equals to r. Okay. And then after that, we continue with row 2. So from row 2, you have x2 plus x3 minus 4x4 equals to 2. Okay. So if you rewrite, you will get this. Okay. So x4, I don't know. We already assume x4 equals to r. And then x3 equals to this. So you substitute all this into this equation. And then you simplify, you will get x2 equals to -1 minus 3r. Okay. Same thing for row 1. Row 1, you have x1 plus 2x2 plus 3x3 plus 5x4 equals to 9. So simplify, you will get this. Substituting x2, x3, x4, what you already obtained here, into the equation, simplify, you will get x1 equals to 2 plus 4r. So in this case, this is called the many solution. Why many? Because r can be any real number. Okay, from negative infinity to infinity, many. And one characteristic for many solution is if you look at the matrix here, this matrix, number of variables is greater than number of non-zero rows. So in our case, number of variables is 4. Number of non-zero rows is 3. So 4 is greater than 3. So in this case, we will have a many solution. Okay. Next is the third case, no solution. No solution is when you have something like this. You have 0, 0, 0, 0, 3. Yes, Wong, you want to ask a question?
No, 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 no.
No. Okay. Okay, I'll continue. No solution is something like this. What it means by this is, remember this is the, let's say the variables is x1, x2, x3, x4. So this means 0, x1 plus 0, x2 plus 0, x3 plus 0, x4 equals to 3. But the left hand side is always equals to 0. We know that 0 is not equals to 3. Okay, so this is impossible. So then this case is known as no solution. Okay, any question so far? So we have three types. One is unique, one is many, one is no solution. Okay, so we continue with the example. So using Gaussian elimination, solve the following linear system. So given any linear system, what you need to do is, first step, you need to form the augmented matrix. So this is the augmented matrix. So for Gaussian elimination, you need to reduce this into REF, to reduce it into REF. So this is how we do it. Okay, sorry, this is the correct one. Okay, so you have the augmented matrix. Now this is already one leading one, so okay. Next step is transform these two into 0. So by using these two row operation, so after that, we need to swap. Why we need to swap? Because if you look at the row 3 here, this is multiple 5, multiple 5, multiple 5. So because we want the first non-zero to become 1, so it will be easy if I swap row 2 with row 3 and then divide by 5, so that I have 0, 1, 2, 4. Why we do that? Because we want to use whole number as many times as possible. If let's say you don't want to do this, you want to divide, you want to keep using the original row 2. If you look at the row 2 here, this is 7, this is 4, this is 2. So the next step is you want to make this 0. How you do it? You divide by 7. So if you divide by 7, this one will become fraction, this one will become fraction. So as I said before, we try to avoid fraction as much as possible. If you insist on using fraction, it's okay, you can continue. So meaning you go back home, you try, you can still get the answer. But it's just that you will you will make the careless mistake a lot easier if you deal with fraction. But you are at home, I know, after class, okay, not now. Very funny, you. Okay, so you go back, you try tonight. And then, so why did I stop? Okay, okay, so I stop here. So we want to make this 1, okay, it's easier. We want to use the whole number here. So the next step is, we want to make this 0. Okay, so using this row operation, you get this. And then divide by 10, you get 0, 1, 3. Again, this is a row echelon form. So this is not unique. Okay, this is not unique. If you don't believe me, you go back, you try use use this one, you divide by 7, then you get a different RDF. But your solution is still the same. It's just that RDF is different. So once you obtain the RDF, you do back substitution. Back substitution means you solve third row first. So this one we use XYZ, right? So XYZ. So third row Z equals to 3. From here you get the Z equals to 3. Then after that you move on to the second row. So you have Y plus 2Z equals to 4. Then simplify, you get Y equals to -2. Then lastly with first row, then X equals to 1. Okay? It's nothing difficult basically. Linear algebra is nothing difficult. It's just calculation. Last semester discrete maths, no calculation. This semester a lot of calculation. Okay. Next is the another example. Again, using Gaussian elimination, solve the following linear system. Again, given a linear system, first step you form the augmented matrix. Okay. Then after that, you need to reduce it into REF. Okay. So the first one is already leading one. Okay. So settle. Next is I want to make this 0, 0, 0, 0. But this one is already 0, so no need. This one, third row, okay already. So we have 2 row operation only. So this is for row 2. This is for row 4. Okay. So you get this. And then you obtain this is 0. So what we do is we swap. We swap again. In this case, I swap row 2 with row 4. Okay. And then you obtain this one. So after you swap, you obtain this one. Then after that, you divide by 30, you get this. And then you do the row operation to make this 0. Then you get this. Okay. So the final row is 0 rows. So we don't look at it. So we only look at the first 3 rows. So this is x1, this is x2, this is x3. So from here, using back substitution, you get x3 equals to 2. Okay. And then after that, move to the second row. X2 minus 2 minus 2 over 3 x3 equals to 8 over 3. So substitute x3 with 2, you find that x2 equals to 4. Then after that, lastly, you have x1 minus x2 plus x3 equals to 0. Okay. Substitute x2, x3, you get there's an answer here. Okay. So you get the answer here. x1 equals to 2, x2 equals to 4, x3 equals to 4. So this is the solution for the linear system. But of course, I'm not sure whether you can check the solution using your calculator. Maybe you can try check. I haven't used the scientific calculator for a long time already, so I don't know the model you use right now. So maybe you can check your solution using your calculator. Okay, next is the Gauss-Jordan method. Gauss-Jordan method is similar to the Gaussian elimination. Just that you want to reduce the augmented matrix into RREF. Okay, So we are using the same example. So we continue from where we stopped just now. This is the REF. So the next step is I want to make this 0 and this 0. So this is the row operation to make this 0, and then another row operation to make this 0. So one good thing with RREF or Gauss-Jordan method is that from here you can get the solution directly. So this is x3 equals to 3, and then x2 equals to -2, x1 equals to 1. No, for the back substitution, there is not much calculation anymore. Okay. Next is the homogeneous system. Okay, homogeneous system is in the form of Ax equals to 0. So everything on the right side equals to 0. It's the same thing. First, you need to form the augmented matrix. It's just that here everything is 0. The steps are the same. So in this case, I want to transform it into RREF. Okay, so this is leading one. Okay, and then this is, I want to make this 0, 0. So then you have two row operation. And after that, this is 1 already. Then the next one is this one. Okay, next one is I want to make this 0. Okay, then I use this row operation to make this 0. Then after that, I want to make this positive 1. So you multiply row 3 with negative, so you get positive. Then after that, you want to make this 0. Then you need these two row operation, and then lastly this is 0. Then you have this operation. Then from here, if you look at the number of columns, so you have 4 columns, 3 non-zero. So again, this is a many solution. So this is x, y, z, w. Okay. So from the third row, you have z plus w equals to 0. So z equals to w, so negative w. So I don't know what w is. So what I do is you let w equals to r, any real number. So in exam, make sure you write this part. Any real number. You must have any real number. R is any real number. Otherwise, you don't get full mark. So W is R, any real number. So then Z equals to negative R. Okay, so Z equals to negative R. So after that, you go on to the second row. Second row is Y minus W equals to 0. So Y equals to W equals to R. Okay. Then after that, first row is X plus W equals to 0. So X equals to negative W equals to negative R. Okay, X equals to negative R. That's it lah. And again, this is one way we do it. Okay, another way we do it is using. I'll just explain. I'm not going to show you because not much space here. Another way you do is okay, from here, this column you settle already, and then this is DD1 you settle already. The following step, this one is okay lah, correct lah. You make this 0, then you have this. but you can also combine directly. You want to make this 0 so that your work is shorter. So meaning you will get the new one. Later you go home try the new value for row 1 by using this row operation. So negative row 2 plus row 1 plus replace into row 1. Okay, so 0 plus 1, this one still 1, and then negative 1 plus 1 you get 0, negative 1 plus 1 you get 0, and then 0 plus 1 you get 1, and then this one is 0. It'll be faster. Okay. Then the next step you go on from here. You try from here. It'll be faster. Here, this one, for example, set we do it one by one so that it's easier for you to see. Okay. So that's the homogeneous system. Another one is using Gaussian elimination. So Gaussian elimination is you reduce it into REF. Okay, so the first step is form the augmented matrix, and then now if you look at the first column, so you have 1 here. So I want to swap with row 1, so that I have 1 here. Now, if you don't want to swap, also can. What you do is another alternative solution is row 1. You replace row 1 with half row 1, but then you will involve fraction here. So that's why normally we don't do that. We just swap the rows that already has 1. It's easier. Okay, so you can go back and try after this. Try. So after that, now here, this is already 1 settled, and then the next step is I want to make this 0. So that's why I have another 2 row operation. So you obtain this, and then I want to divide this by 5. Okay, so you get 1. The next step is this to make 0, because now this is RDF, so 0. So this is 0 operation, you get 0. Then here it becomes fraction. Never mind, I want to divide it by this, and then to make this 1. Then you get the solution. So from here, remember this is x, this is y, this is z. So from the third row, z equals to 0. Okay. And then from the second row, you have this y plus 3 over 5 z equals to 0. But z is equals to 0. So this term equals to 0. So y equals to 0. And then since y is 0, z is 0, x is also 0. Okay. Now, last subtopic is the finding inverse. Okay. So finding inverse using row operation. So one way to do that is first you write down the partition matrix A / identity matrix. So this is the identity matrix. Remember the notation, identity matrix. Okay. Then transform the partition matrix into identity matrix / A inverse by applying elementary row operation. Okay. Note you need to take note is that if at any point in the computation we transform A / identity matrix to RREF, obtaining CD where this is not identity, then D is not the inverse matrix. In that case, we say that A is singular. A singular means there is no inverse matrix. For example, here, given A is this matrix, find the A inverse. Okay. So first step, you form a augmented matrix. So the first part is matrix A. The second part is the identity matrix. Okay. Again, you do the row operation. What you do is you want to transform this matrix into, this is identity matrix on the left hand side, and then you have a value, you have another matrix here, and then this will be your inverse matrix. So how we do this, the transformation, you use row operation. So we do again column by column. So this is already one settled, and then I want to make this 0. Okay, so 0 0 using these two row operation. And then after that, if you look at the row 3 and row 2, row 3 and row 2, they are actually multiple. So by multiple of 4, so meaning if you apply this row operation, you can transform row 3 into 0 0 0. So when it becomes 0 0 0, this one definitely will never become an identity matrix. Okay, because we want it to be 0 0 1. We want it to be 0 0 1. But if you obtain something like 0 0 0, definitely not an identity matrix. So in this case, you can stop here. You can right away make your conclusion. You say that since the matrix B, okay, so in this case, we label this part as B, this part as B, matrix B. So since B has a row of 0 and B is not identity matrix, we straight away conclude that A is a singular matrix, meaning you will never find the inverse matrix. This is one example. Another example is where you can find the inverse matrix. Okay, given a matrix A, and then first you form the partition matrix. This is A, this is identity matrix, and then you do the row operation. Row operation means, okay, so this is leading one, okay, and then you need to make this 0 using this row operation. So you will obtain this. So after that, I need to make this 1, I need to make this 1. So I use these two row operation. Then you get 1 1. Okay. Then the final step is I want to make this 0, I want to make this 0. So the first step is we do the third column first. So using these two row operation, you get 0 0. And then finally you want to make this 0. So then you manage to get the identity matrix on the left hand side. So once you obtain the identity matrix on the left hand side, then you can conclude that on the right hand side, this is your inverse matrix. Okay. So row operation can be used to find the solution of a linear system, can also be used to find the inverse matrix. Okay. Any question? That's the
so far no questions.
that's the final slide. Okay, if no question, then thank you. Later on, I will share the QR code again. So if no question, then if you already scanned the QR code, then you can leave. Go back and try again the alternative solution that I mentioned just now. Because for the RDF, you need exercise, you have to do exercise, otherwise you are not able to do it in a sense. Okay. Okay, Lucas, you raise hand. Any question? Oh, okay, misclick. Okay, good. So I will reshare the QR code.